Protection Partnership. We're going to have a great discussion on freshwater salinization today, a topic that's particularly relevant right now given the amount of freezing rain and snow that we've gotten over the past several days. I watched a truck driving down the street past my house yesterday with its disc spinning back and rock salt flying everywhere, and you realize that all that salt is eventually going to end up in the stream right down below my house. For those who don't know me, my name is Greg Bush. I joined the water supply program at MDE several months ago. Prior to being in the water supply program, I worked in MDE's water planning group, where I developed watershed restoration plans for Maryland, including our phase 3 WIP for the Chesapeake Bay for reducing nitrogen pollution into the bay. Worked on TMDLs for sediments in our streams and PCBs in our estuaries, and then worked on language in the MS4 permits, including new language to require salt management plans in our urbanized areas in the state. I think apart from the recent snowfall that just happened, this is also a good time to talk about salt, because while we have all these great new de-icing technologies that offer a lot of potential, I think there's a recognition that the salting technologies alone are not going to get us to a place where we need to be for salt, and that the expectation of a certain level of service on our roads will always be at tension with our need to protect our drinking water sources, and we're going to have to figure out how to deal with that. There's another technology that I'm thinking about that seems to me that could be important in the coming years, and that's with the COVID restrictions in place these days. We've all become more comfortable with virtual meetings, and we've all become more comfortable with working from home, and with the fact that we don't necessarily have to see people face to face in order to get our jobs done. And maybe this technology and maybe this level of comfort will have a sort of ripple effect in us rethinking how do we balance the need to get the roads cleared against the applications of salt into our environment. This is not going to be a quick transition. It's going to be sort of more of a broad societal shift in thinking. But I think at the very root of it comes this a need for a foundation of strong science and education. And I think that's where organizations like the Source Protection Partnership come in. Since 2004, the issue of road salts has been an important topic of interest for our members, and this is something that's been reflected in our work plans. The partnership has become more educated in various aspects of saltwater salinization, and we're understanding that although road salts are a major issue, it's not just it's not the only issue. And I think it's important to note that in the last few years, we've had a bunch of regional efforts in the Washington, D.C. metro area that have started up to help us better characterize salts and understand their impact on freshwater systems. So that's where we're at today. Just our discussion today. So since arriving from UC Irvine a few years ago and assuming co-directorship of the Aquacon Watershed Monitoring Lab at Virginia Tech, Dr. Stanley Grant has embraced the challenge that salts present to the Mid-Atlantic region, immediately taking on several initiatives to better characterize sources of salinization. Many folks in the partnership have worked on salinization, participate in research with stakeholder discussion that Dr. Grant facilitated back in January of last year. We're excited to hear about his research and thank him for his leadership and commitment on this issue. So with that, I'll provide formal introductions. Dr. Stanley Grant is a professor in the Department of Civil and Environmental Engineering at Virginia Tech, co-director of the Occoquan Watershed Monitoring Laboratory in Northern Virginia, and emeritus professor in the Departments of Civil and Environmental Engineering and Chemical Engineering at the University of California, Irvine. Dr. Grant's professional interests include the measurement and modeling of pollutants in coastal and inland waters. Dr. Grant received his BS with distinction in geology from Stanford University in 1985 and his MS and PhD in environmental engineering science in 1990 and 1992, respectively, from the California Institute of Technology. He'll be joined by Dr. Marc Edwards, who is a University Distinguished Professor of Civil Engineering at Virginia Tech, where he teaches courses in environmental engineering, applied aquatic chemistry, and engineering ethics. His research group conducted an investigative science uncovering the 2001 to 2004 DC lead crisis and the 2014 to 2016 Flint water disaster. The White House awarded him a Presidential Faculty Fellowship in 1996. He won the MacArthur Fellowship in 2007. And in 2013, Dr. Edwards was the 9th recipient of the IEEE Barris Award for courageously defending the public interest at great personal risk. He was co-recipient of the inaugural 2017 MIT Disobedience Award, received the 2018 AAS Scientific Freedom and Responsibility Award, and the Hoover Humanitarian Medal in 2019. So let's welcome them all to our meeting today.
Thank you, Greg. Stan, I am going to give you screen share capabilities. You should see a prompt on your screen.
There you go, Dee Dee.
There you go, you're all set.
Cool. Thank you. Thank you, Greg, for the nice introduction. And both Mark and I are thrilled to be here today to share a little bit of the research activities that are going on at Virginia Tech related to salt management. And we've decided to call some of the efforts anyway related to the Occoquan Lab an initiative to reverse freshwater salinization, or REFRESH, which may be the best thing about the project that I'm working on anyway, is the acronym. So here's the outline for the talk. I wanted to first talk a little bit about the vision for this REFRESH effort, and particularly how the Occoquan Lab fits into that. Some of the progress so far, focus on a new NSF grant that we got through the Growing Convergence Research, or GCR program at the National Science Foundation. And we just found out yesterday actually that Nature Sustainability paper on the salinization issue, co-written with a number of folks, including some of the folks on this call, was accepted for publication. So I kind of want to walk through that as it reflects some data collection in the local area here. And then talk about some of the next steps on the GCR grant and Moonshot Initiative to land an engineering research center, which is a $50 million NSF-funded activity. So anyway, that's we'll kind of blaze through that in the next 40 or so minutes. And again, Marc Edwards and I will be team tagging their presentation. And so, you know, when I came from Southern California to Virginia and assumed the co-directorship of the Aquacon Watershed Monitoring Lab, one of my duties or the reasons for being here were to think through ways in which the Aquacon Lab could work together with the Department of Civil and Environmental Engineering at Virginia Tech, which is a top 10 engineering program, as I'm sure many of you know, to secure private, state, and federal funding to do something really special at a national scale. And it very quickly, within the first year or so, I found that focusing on the freshwater salinization issue was likely to have a lot of traction across both the Department of CE at VT, because we have so much breadth and depth of expertise in that area, as well as with the stakeholders that have been working with the lab for going on 40 or more years. So anyway, from a kind of from my professional perspective, this is the vision, really joining up the Aquacon Watershed Monitoring Lab in Manassas with the CE department in Blacksburg to really do something special at both a local and national scale. Our progress so far, you know, we have a kind of laundry list of things that we've been working on. We did receive very early on an NSF ERC planning grant. The ERCs, again, are the $50 million activities, and they've been giving small, well, relatively small planning grants to try to encourage engineering researchers to get their act together on that. And so we received one of those, some local funding, and I think, as Greg mentioned, I, along with other colleagues, ran a freshwater salinization workshop at Fairfax Water, really in January 2020. It's hard to believe after this. Seems like it's been about 10 years since January 2020, doesn't it, with COVID? But anyway, that we had about 100 attendees from really across a broad spectrum, and that became the impetus for putting together an NSF grant to the Growing Convergence Research Program. And we were awarded $3.6 million out of that just a couple months ago. So that was kind of our first step, I guess, toward maybe having a center scale activity. We've been working with COG also to develop partnerships, including one that co-funds Virginia Tech with the USGS and the University of Maryland. And we submitted an ERC sort of pre-proposal on Refresh back in October, and we should be hearing whether we're going to kind of make it through that screen, the pre-proposal screen, in the next couple of weeks. So I wanted to tell you a little bit about the NSF GCR grant, and then segue into the Nature Sustainability article. So kind of go from there. So the GCR program at NSF is a agency-wide program, so it covers all areas of science and technology engineering that NSF funds. And so it's extremely, translated, it's extremely competitive program. It's one of NSF's 10 big ideas, this idea of bringing lots of different disciplines together to tackle big societal grand challenges. Again, our award is on this is up to $3.6 million over 5 years. I'll explain what the up to means in a minute. Virginia Tech is lead, I'm PI, but we have money going to University of Maryland, North Carolina State University, and Vanderbilt University. And you can look at the co-PIs there at the bottom and get a sense that we're quite a diverse group. So Tom Birkland is a social scientist at NC State. I think you all know Mark. Jesus Gomez-Valles is a hydrologist at Vanderbilt. Aaron's a biologist, microbiologist at Virginia Tech. Sujay Kaushal is a geochemist at University of Maryland. Meg Rippey is an engineering ecologist here at VT. Todd Schenk is another social scientist at VT. Peter Spexland is a professor of environmental engineering at VT. And Kristen Rowles is a facilitator. I think many of you know Kristen. So anyway, it's a really diverse group of people, kind of an unusual collection of co-PIs. And that really fits with the theme of the Convergence program, which intends to integrate knowledge, tools, and ways of thinking across disciplinary boundaries to form a synthetic framework for tackling scientific and societal challenges. So NSF actually did try to define convergence. There's a lot of kind of hand-wringing about what exactly it means, but here's one definition. In our context, we're really arguing in the proposal, we argued that our convergent piece is the idea of using Elinor Ostrom's common pool resource theory. So Elinor Ostrom won the Nobel Prize in economics, but she was a social scientist. And she took on this notion of the tragedy of the commons, which basically, in short, says that when you've got a common pool resource like a groundwater basin or freshwater resources that are accessible to everybody, lots of different users, that you have to implement regulations or top-down control, otherwise those users are going to deplete the resource. And so basically, she looked at lots of case studies around the world and found that there's lots of examples where that's just not true, that local users can organize in the absence of any top-down regulations and manage their own resource just fine. And so she developed a set of, not really criteria, but kind of guidelines for conditions under which that might actually happen. And so our goal is basically take those guidelines and apply them to so salt management in the Occoquan Reservoir to see kind of how far away we are from co-managing that the salt buildup in the reservoir, with just the local users cooperating as opposed to DEQ or some other agency coming in and regulating the problem. The grant itself, we were required to break it into 2 phases, and the idea being that the phase 1 activities, we get 2 years of upfront funding, to focus on that. And we decided, because we had some experience looking at UOSA's, the Occoquan Authority, we had some experience looking at their salt contributions, and we would focus on that during phase 1. Then after the first 2 years, we go to NSF for a reverse site visit in June 2022, and basically we present the results of our findings. They make a assessment whether we're going to get the rest of the funding, sort of phase 2 funding, and at that point we would turn from UOSA to, or at least add to the focus on UOSA, the Occoquan and Bull Run watersheds, and look at their contribution to the salt budget as well. So one of the things I wanted to share with you is, kind of an initial look at the salt contribution of the Upper Occoquan Service Authority, or UOSA, which is described in this Nature Sustainability paper, which will be coming out. We just found out yesterday that it was accepted for publication. And so we, one of the things I wanted to point out, and I hope that we do this more and more, is that the list of co-authors here represents a really broad cross-section of folks, from graduate students and professors to people like Greg Prelowitz and Niffy Saji from Fairfax Water, Shannon Curtis from Fairfax County, and so on, social scientists. And so basically bringing together a lot of folks with the idea of not just describing the problem, but also perhaps laying out scenarios for its solution in the future. And so basically, just to orient ourselves, I think most of you know about the Occoquan Reservoir, but we're essentially focused on the reservoir itself and the Occoquan Dam here, just upstream of the Potomac River. And the Occoquan Reservoir is receiving water from Bull Run and the Occoquan River. And we have the lab, the Aquacon Watershed Monitoring Lab, has long-term monitoring stations at ST10 on the Occoquan River and ST45 on Bull Run, downstream of UOSA's reclaimed wastewater discharge. And here's a graph just showing some of the data that we collected from the Fairfax water intake, from Fairfax water monitoring programs. So that's the purple curve there. And we're looking at sodium concentration on the vertical axis on a log scale and versus time from 1980 to present. And you can see, and I think many people have seen this before, that it looks like there's a rising trend in the sodium concentration at the dam, at the water intake, and that rising concentration is such that now relatively frequently we're exceeding the sort of EPA health advisory and the lower taste thresholds for sodium. If you look at some of the other historical data, so these are just data, there's no models or anything. So ST45 downstream of UOSA, well, you start with UOSA. So basically the data we have from UOSA, basically some of the highest concentrations we've seen on the monitoring station data that we have. Downstream, it looks a little bit more dilute, like maybe it's mixing with the water coming from Bull Run upstream. And then the Occoquan River is shown in yellow. It's actually a relatively undeveloped watershed, and it's indicating here kind of one of the lowest of the different stations that we looked at here. So basically, you see this kind of ordering where UOSA at least has the potential to contribute fairly high concentrations of sodium, but not necessarily high loads of sodium. So that was one of the purposes of the article, was kind of focus in on under what conditions the UOSA contribution in this case is a significant fraction of the sodium load going to the reservoir from Bull Run and the Occoquan River. And one of the ways that we did this was we basically took all the historical data and put it on kind of an apple-to-apple comparison through the use of multiple linear regression models that predicted sodium concentration and sodium load on a daily basis from the UOSA plant, from Bull Run upstream of the UOSA discharge in the Occoquan River. And from that data, we were able to construct, using what's called a Copula Analysis, probability distributions of the percent sodium load coming to the reservoir from these three sources under different weather conditions. So under wet weather conditions, as you might expect, most of the sodium load is actually coming from the relatively heavily developed Bull Run watershed, less from the Occoquan River, and then the smallest fraction is from UOSA itself. And the way to read these graphs is not the peak. The peak doesn't mean anything. It's the range over which you have non-zero probability, because the peak just is determined by the unit probability under the curve there. So that's under wet weather. But when we go to dry weather, we see the situation flips a bit. Perhaps not surprisingly, we already saw that UOSA has fairly high effluent has fairly high concentrations of sodium, and also one of the benefits of UOSA is that it provides a significant fraction of the water coming. It basically protects the water source from drought, right? And so if you get high concentrations and high flow, relatively high flow during dry weather conditions, it's not surprising that UOSA would contribute during those periods a fairly high sodium load to the reservoir compared to either the Occoquan River or Bull Run. Nevertheless, I think that this might be surprising to some folks who, when we're in the mid-Atlantic region or in the Northeast, the first go-to thought is that in fact, most or all of the freshwater salinization problem is coming from Deicers. And when we started thinking about where that sodium, in UOSA's effluent might be coming from, it's a bit of an Ouroboros if you're familiar with that, a snake that eats its tail, because there's just myriad sources. And if you think about it, UOSA becomes kind of a funnel through which all of those myriad sources end up moving into the reservoir. And just to give you an example, so we worked with the stakeholders in the region to kind of map out a flow diagram, so where does the water from that goes into UOSA come from? And obviously we've got sources from Lake Manassas and the Potomac River, and of course we have de-icer inputs and other sources of salinity or sodium moving into those natural systems. Then that water goes through treatment plants, and of course there's additional sodium added during that process, and Marc is going to talk a little bit about that in a minute. And then it goes through the retail and wholesale customer distribution systems, and we're going to get households adding a lot of sodium or other salts through the down-drain disposal of commercial products that they use, soaps and so on. And then also industrial, commercial, and permitted discharges coming in there. And then that all goes to UOSA. UOSA has to add additional sodium for some of its treatment processes, goes to the Occoquan Reservoir, which also then receives salt and sodium from the watershed, goes to a drinking water treatment plant, and again, there's salt added through the treatment process, and there's a potential to send the water back through kind of a big loop, although in most cases it's just a one pass-through system. So, in fact, trying to get a handle on or trying to reduce the sodium load coming into UOSA and then ultimately from UOSA to the reservoir is really, you have to look upstream and start thinking about who are the major contributors to that sodium load, and how would we potentially reduce their contributions. And I guess the other thing I had here was just a little picture showing that if you look at the sodium mass load coming out of UOSA's effluent here, that you can attribute a certain fraction to these various activities like water treatment from the drinking water plants. There's a microfab facility that contributes a certain amount. I think that's 13.8% here on an annual basis. You can make estimates for sodium addition by human excretion from literature and knowing how many people are in the sewer shed. Wastewater treatment processes themselves contribute about 15% for dechlorination primarily, I think. But there's a really big fraction of this which we don't actually know. And my guess is a lot of that is sort of household contributions within the sewer shed. But some of that's going to be salt actually contributed by the water itself from de-icers and so on. So even when you're focusing, I guess one of the bottom lines here is that even when you're focusing on UOSA's contribution, in fact, it includes contributions from de-icers, so you can't get away from the sort of salt application that goes on in the watershed as well. So like I mentioned, one of our goals in writing the paper and a lot of our products going forward is not just to sort of elucidate problems, but try to map out pathways by which they could be addressed and solved. And so in the paper, we argued that, really this may boil down to producing what we call salt productivity, which economists would, I guess, define as goods and services produced per unit of salt discharged to the environment. In other words, we're not going to completely eliminate the discharge of salt to either the sewer shed or the watershed, but maybe we can, we can reduce that amount of salts that are used essentially to get all the goods and services that we expect in society today. And ways in which we might improve salt productivity include some of the obvious, like reducing watershed sources of sodium that end up in the water supply. And so I think that's kind of on everybody's mind, like for example, from Deicers, especially with the weather we've had the last week or so. But also we could look at more stringent pretreatment requirements on industrial and commercial discharges within the sewer shed. We could start thinking about switching to low sodium water and wastewater treatment methods, and Marc's going to be talking a little bit about that. But we could also look to the households and maybe use social marketing methods to induce or entice them to move toward low sodium products and practices. And so through the project and some of these longer term efforts, we'd like to try out all of these, basically have formal control trials to see which one works best. So with that, I think I'd like to turn it over to Marc, and he can talk about some of his research on this topic.
Excellent, thanks, Stan. And this is really an opportunity to kind of shift gears. And of course, with salinization, there is the fact that you have in salt a positive ion, i.e. sodium, and you also have a negative anion. That's the flip side of the coin, and in this case, it's chloride. And we first got interested in this issue, it was 2014, not only in relation to Flint, when they switched water sources, they went from a low chloride source water to a high chloride source water, which triggered problems. But we'd also had many utilities calling us who'd never had colored water problems before, who in winter months when chloride was spiking due to salt application to roads, they were suddenly getting consumer complaints. And in the Potomac at WSSC, chloride levels were spiking from typical values around 40 up to 400. So these are 10x spikes in chloride. And chloride is what we call a corrosion determining ion, which means oftentimes the rate of infrastructure degradation and metals degradation is proportional to the level of chloride. And then we also had an interesting thing in 2015 where brick utilities, which had for decades had undetectable lead in their water, suddenly started reporting catastrophic levels of lead in the hundreds or even thousands of parts per billion due to lead solder. And what had happened was the road salt had increased the chloride level in their water slowly over the years and just pushed it over a threshold that created catastrophic failures. Next slide. So when we got those reports, we started studying this and sort of realized the obvious, that chloride levels are rising across the country, not just due to road salt application, but also due to use of sodium chloride softeners and rising sea levels and saltwater intrusion in coastal areas. And this worried us because in many cases, infrastructure degradation is proportional to the level of chloride in your water. And the fear is we're going to be destroying our already decrepit and antiquated infrastructure faster than we were previously. It's also interesting to note that unintended consequences in some parts of the country due to good control of atmospheric sulfate levels and use of lower sulfur coals and reduced coal burning, that sulfate inputs to watersheds is plummeting. And so, that if you advance, somehow I can't see the whole slide. Can you advance it? Yeah. So the net result is chloride's going up, sulfate's going down, and this is a problem because in some cases corrosion, galvanic corrosion, is controlled by the ratio of chloride to sulfate. So next slide. The reason we care is because this affects our customers and our billions, hundreds of billions of dollars of water infrastructure. There's a lot of cases where so-called galvanic corrosion, which is when you have two metals connected together, control the satisfactory performance of the material. And these are present in many residences, and I'll just mention a couple. But first and foremost, through 1986, lead solder was used to connect copper pipes. So this is a major source of lead in many water supplies. But secondly, our water heaters, which are, a very expensive element of our hot water infrastructure and buildings, their lifetime, their longevity is dependent upon the performance and lifetime of aluminum or magnesium anodes that are in these water heaters. And those anodes are most typically made of aluminum or magnesium. And so basically you're connecting aluminum or magnesium to your steel tank. And although it has a glass liner, there are holes in the liner. And as the aluminum magnesium corrodes, it protects your tank and allows it to survive. And generally speaking, once that anode is gone, your tank is going to fail oftentimes within a matter of weeks or months. And the other issue was, we had this issue of just spiking lead levels. And if you go ahead, it really got us concerned about the infrastructure damage. And one of the eye-raising points that was made in the workshop that Stan organized and others participated in is that based on the best available current estimates, each dollar of road salt that we apply results in about $46 in infrastructure damage. So I'll repeat that just in case anyone missed it. Every dollar of road salt we pay to put on our road is estimated, according to current studies, to cost $46 in infrastructure damage. And when we looked at this, we realized it didn't include any estimate of the damage to private or public plumbing. So, this might very well be an underestimate. So if you go to the next slide. So we had this case in Orleans, New York, where chloride levels had been rising for a period of decades, and consumers who had water heaters lasting 10, 15 years, as is normal, were suddenly having to replace their water heaters in less than a year. And some of these wells were downgrading of a salt barn, and this has been written about in the paper. Eventually, these private well owners got connected to public water mains, and even with a subsidized grant, these well owners are having to pay $900 a year for 30 years for the privilege to just not having salt water. So not only have they lost their asset of their well and the aquifer, but they have to pay to just get water from the town. So next slide. And so we wrote on this, and it was published in ES&T in 2018. If you go to the next slide. So we did some initial studies to just kind of ground truth the citizen science, the observation of these consumers. That is, how bad is chloride in terms of galvanic corrosion of common galvanic couples that we rely on to protect infrastructure? And is there any way that inhibitors can reduce the impacts? And so the four common galvanic couples we looked at, of course, lead, solder, and copper. That's, again, the major source of lead from copper plumbing. And then we looked at iron and zinc because you have a lot of galvanized iron infrastructure out there. So galvanized is zinc-coated iron, and once that zinc is gone, you're going to have all kinds of problems with that material. And then we looked at the water heaters, which is iron and manganese galvanic couples and iron and aluminum. And we looked at a suite of corrosion control inhibitors just to say, hey, is there anything we could do to stop this higher chloride? And if you go to the next slide, keep going. Next slide. Great. So what this graph shows in the bottom is the level of lead leached to water. And this is a simulation of a DC area utility, but we see the control condition, which is with low chloride. And then you see what happens when the road salt is increased as it occurs during a spike, during a winter storm, kind of like which we just had. And that rising chloride led to a 14x increase in lead in drinking water. And then as you look at the zinc ortho and zinc ortho, what we're looking at is, are any of our standard inhibitors doing anything to stop this attack from the road salt? And so what you can see is that, yeah, it looks like zinc might be able to reduce it a little bit, although you're about 7 times worse off than you were with low chloride. And ortho and zinc ortho didn't really help at all. So this is the essence of the problem, is that we've got rising chloride and problems associated with that are going to directly affect consumers and potentially their health. And short of getting the chloride out of the water, we're uncertain about how to stop this problem. If you go to the next slide, it's even more dramatic. This is a visualization of what happens in your water heater. So on the left-hand side, you have your magnesium anode, and it's electrically connected to, on the right-hand side of each picture, which is your steel representing your water heater tank. And the current, of course, the magnesium is sacrificed. And as you go from left to right here, what you see is the control, and this is over a very short-term time period. And your anode lasts, and it's sending electrons to protect your steel. And at low chloride, your anode in a water heater tank can easily last 10, 15 years. But if you look at what happens with the higher chloride water, we lost virtually all the magnesium in a short period of time. So this really illustrates the nature of the problem. And if we'd continued this test, once the magnesium's gone, your iron tank is going to start disappearing too. But you can see some benefits of the inhibitors for this galvanic couple, in that with orthophosphate, there's a little tiny bit more, not much, of your magnesium left. And as you go to orthophosphate and zinc orthophosphate, you're getting longevity. So what this simple, results have illustrated is that chloride's bad, really, really bad. Sometimes we can reduce the damage by adding inhibitors, sometimes we can't. And so if you go to the next slide, if that isn't bad enough, when these anode rods corrode, they release hydrogen. And of course, hydrogen is what did in the Hindenburg. There have been cases where water heaters have actually released enough hydrogen that they can cause an explosion. This is very, very rare. But the bigger concern is hydrogen is an excellent food source for bacteria. It supports an autotrophic food chain, food web, right in your water heater where you don't want it, because you have ideal growth for pathogens such as Legionella. And so we've shown that the higher chloride is very likely to create more problems with Legionella in water heaters as well, which makes this a very significant public health concern. And I think we're all familiar with the idea that sometimes hot water smells. It smells like rotten eggs, and that comes from hydrogen sulfide. And for years and years, people have been trying to get around that problem by replacing their magnesium anodes with aluminum anodes, but that won't work. Even that won't work for that aesthetic problem if chloride levels get high enough. So if you go to the next slide, there's a lot to worry about here. We're losing our infrastructure by putting the salt on the roads, and we have to figure out a way to either reduce the salt or reduce these impacts, because we're already kind of going bankrupt maintaining our existing antiquated infrastructure. Chloride definitely does exacerbate the degradation of infrastructure, and especially for galvanic couples. Sometimes inhibitors can help, Go ahead, Stan. Next slide. But the biggest concern is really what are the actual costs of underestimating impacts on drinking water infrastructure. So if that figure of $1 paying to put road sign on a road, it's $48 of damage. At what point do we start to reassess whether this makes economic sense? So part of what I want to do here is just educate you all to this, because you're going to be getting complaints from your consumers in the future about these failing appliances, failing water heaters and other water quality problems. And if nothing else, you can say, based on this presentation, it isn't all our fault as water utilities, that there's things that's happening to the water as a result of this process that are going to severely impact consumers, and we can't control it. That's it.
Thank you, Mark. Yeah, fascinating. So, so I guess now I wanted to talk a little bit about sort of next steps on the GCR grant. As I mentioned, we received the funding just a couple of months ago, and so we've been meeting weekly as a research team, kind of getting to know each other. A lot of us have not worked together before, and so it takes a little while for that to kind of gel. And then also just trying to figure out how we're going to perform the magic we need to perform when we go up for a reverse site visit at NSF in a little bit more than a year and a half, and get that second phase of funding. Not to be a martyr about it, but that's obviously a big focus. And so what's been going on too in the background, we haven't just been meeting, we've been starting to collect data and starting to think about how we would demonstrate convergence, which is one of the real major criteria that we have to show to NSF, and also obviously make progress on the salinization issue. And so we, broadly speaking, have a social science team, and then we also have a biophysical team. So you can group the people involved into those two kind of expertise categories. And with the social science team, we want to conduct human subjects research, really understand what people think is the source of the problem, and see where the points of disagreement are, and see if our project can kind of move the stakeholders closer together with the ultimate goal of co-managing this project, or the Aquacon Watershed salt budget, kind of from the ground up. And that any kind of human subjects research requires institutional review board approval. And so it was kind of a long process that we went through the last couple of months to get IRB approval, and we have that now. It just came through. And so basically, we're going to be doing a couple of things on the social science side now that we have that approval. We're going to be conducting interviews with stakeholders to try to understand better their perspectives again, but also generating what are called fuzzy cognitive maps in collaboration with stakeholders. And basically, this is a fancy way of describing how sort of people view a problem. What are the main, in our cases, sources of salinity coming into the Occoquan Reservoir, for example? What are the pathways by which those salinity sources get into the reservoir? And what are the management controls that we could potentially put in place to control that? And so we want to basically create, this is just an example of a fuzzy cognitive map for traffic. Obviously has nothing directly related to do with salinity, but I just put it here as an example. So we want to work with really a large group initially to try to elicit these fuzzy cognitive maps for everybody, kind of a summary of what they think is going on to drive salinity levels. And then we have a way of aggregating those by disciplines. So we kind of look at what people who work maybe in water utilities think are the primary drivers, pathways, and management options versus maybe what folks who work in so the wastewater industry think, and so on. And what these cognitive maps will do is they'll essentially crystallize where the major differences are. And that then becomes a point of discussion with the stakeholders to really try to understand what science the team can do, can bring to bear in order to move those differences, reduce those differences, and accentuate the agreement. So that's kind of the social science side. The biophysical engineering team, meanwhile, because again, we're in the phase 1, so we're really focusing on the sewer shed. We've already started to set up field measurements and modeling to really characterize the ion concentrations that are being released over time from the sanitary sewer system into UOSA, really trying to go back upstream to see where that missing 50% is. And this is just a picture of a portion of Fairfax County sewer shed that drains to UOSA, and our hydrologist, Jesus Gomez-Valles, and his postdoc basically used hydrological principles to break that sewer collection network. So those little black lines there are all the sewer lines that basically connect together and then ultimately drain to the Cub Run pump station here, which is one of the major inputs to UOSA. Basically using hydrological principles, broke the network into essentially subsheds, each of which under sort of average flow condition contributes about 20 liters per second. And so we can start looking at the land use characteristics, sort of, what are the sources of sewage within each of these different subsheds. These could potentially serve as intervention points. So we could maybe identify 1 or 2 different subsheds to run social marketing campaigns, for example, to see if in fact we detect any change in ion concentrations coming out of these subsheds over time. The other thing that we note, if you go to the Cub Run station here and you look at the historical flow data, which UOSA very kindly gave us, not surprisingly, you see a lot of diurnal variability. So this is just a couple week period of time. And the Cub Run station here is in pink, again, flow in million gallons per day on the vertical axis. And you see that middle of the night low, morning peak, evening peak, and then again the middle of the night low. And what we imagine is that what we hypothesize is that the ion concentrations associated with that flow are going to be very, very different. Like the minimum here may actually have a big contribution from groundwater. So just sitting at the Cub Run pump station and sampling hourly over that flow variability, we'd expect to see maybe a larger contribution of groundwater, and then essentially sampling groundwater, at least a portion of it, and its ion concentrations during the middle of the night. Whereas in the morning, maybe we're picking up from human behavior kind of a different ion composition, maybe related to showering and so on. Evening, maybe it's more dishwashing, so on. Anyway, the point is we're going to set up at the Cub Run station, sample hourly over this diurnal variability of flow for a couple of weeks, and then use hydrograph separation methods to essentially determine if we can statistically separate out the ion contributions from 3 or 4 different sources and look at what those look like. We need to know this diurnal variability because if we went up and started sampling these subsheds at their base, the ion concentrations we measure could depend as much on when we sample as where we sample. And so the diurnal variability makes sense to kind of as a place to start. And I'm just showing, we went out with Nathan Wells from UOSA, I think last week or the week before, to kind of scope out where we were going to sample, and we identified a manhole just upstream of the Cub Run pump station, which will allow us to get in and sample this on an hourly basis for probably 2 weeks, with the goal again to characterize the ion composition of the morning and evening flow peaks, as well as that middle of the night minimum, which is primarily groundwater, presumably from EPA literature anyway. One of the things that kind of sampling effort does is it produces hundreds, maybe 300 or 400 samples over the course of the study. And so we're also expanding OWML's analytical capability, and we have this new IC system on its way. The cool thing about it is that it's a very high throughput, so very minimal time per sample. And it can run 24 hours per day. So we have a chance of processing 300 or 400 samples that might come from a study such as this. And the other thing that the biophysical team has been looking at is just looking at UOSA's contribution of salt to Bull Run and the Occoquan Reservoir with some field sampling efforts. So a couple of weeks ago, we went out and in part, the initial efforts are really to get the team familiar with the field sites. So it was a nice opportunity to kind of bring everybody together, do some sampling, The other thing we're trying out is I mentioned groundwater as a potential contributor to salt in the sanitary sewer system. Obviously, groundwater is potentially a significant contributor to salt in the streams as well. And there's a really sort of well documented way of measuring the contribution of groundwater in a freshwater body, and that's by measuring radon 222. And so we also deployed this RAD7 on the boat in the field study that we conducted the other day. And it turns out that the sediments around here are high in radium and actually generate a fair amount of radon 222. So this could be a really great way of kind of sniffing the contribution of groundwater to the ion contributions, both in the sanitary sewer system and also in streams. So anyway, we've got these sort of social science activities, we got the biophysical activities, and we're going to bring them together with the executive committee and the Aquacon Watershed. And we're going to run some additional workshops to develop those cognitive models and explore the sort of areas of agreement and disagreement across the disciplines, with the idea of really co-producing a research agenda and co-analyzing the data as it comes in. So stakeholders are intimately engaged in that entire process. That's the goal. Which hopefully will put us in a good stead for our reverse site visit at NSF in 2022. So, and then I just wanted to finish by telling you a little bit more about the ERC bid. So the basic idea here is that we're taking what we're doing in the Occoquan Reservoir, and we'd like to scale it up nationally and potentially internationally. The ERC proposes to have 3 testbed sites, one in the DC area, one in Illinois, and then also one in Southern California. And so UIUC is leading the testbed in Illinois, and UCLA is leading the testbed in Southern California. And these, this is obviously on this map, you see these red triangles. This is a recent USGS assessment of streams across the nation and whether the stream-specific conductance is increasing or decreasing. And certainly in the Mid-Atlantic region, Northeast, you can see that there's a lot of these streams that are increasing over time. In Southern California, you don't see a lot of red, but that's misleading because there just aren't any streams in Southern California, but they have huge salt issues related to importation and recycling of water there. Our vision statement is to reverse freshwater salinization by transforming the nation's engineered systems for water transportation, agriculture, and resource extraction through cost-effective and sustainable technological and behavioral interventions. So really, it's about improving salt productivity, but focusing in on the sort of engineering infrastructure that Marc mentioned, which is super expensive, very vulnerable, and in many cases is contributing to the problem as well. And all ERCs have to have this DREAD 3-plane diagram. NSF requires it. And I'm just going to blow through this, but basically the idea is that each of these test beds, we would start with working with stakeholder engagement, and that's what the SET stands for, stakeholder engagement and translation, to basically get local knowledge about what the sources of salinity are, and kind of where the priority lies in terms of getting a handle on that, leading to experiential knowledge. And then we bring in the scientists, the geochemists, the stream ecologists, and engineers and so on to try to characterize, merge that experiential knowledge with technical knowledge about the sources and the pathways by which the salt is getting into water of concern. And then basically that information feeds into a sort of investigation of the possibility space for interventions from centralized systems like changing up the way that we treat water and wastewater, to more granular interventions like social marketing campaigns at the household scale to get people to use low sodium or low salt products. The barriers here include engaging diverse stakeholders that we're going to try to overcome, merging the biophysical and social data, and agreeing on interventions. That intervention possibility space is then goes through a sort of information technology approach where we're comparing granular and centralized interventions, so we try to scale that up and compare apple to apple, which ones are most likely to give us our biggest bang for the buck, leading to what we call an intervention frontier, which is then evaluated from the perspective of sort of human impacts, sort of ecosystem and environmental impacts, as well as big portion of the ERC is, can we sustain the technology that we're developing in a profitable way, leading intervention trials, and then eventually going back to the stakeholders to see which of these results are kind of the most promising, and actually ideally leading to IP licensing and the formation of startups and so on that go out and do this, not just at our 3 testbed sites, but nationally and internationally. And order of operations. So again, I mentioned we submitted our pre-proposal back in October. They're probably, the estimate I heard from one of my colleagues was that NSF receives about 1,000 of these pre-proposals across the country. And they whittle that down to probably 50 bids. So it's a really steep drop. But we should hear on our pre-proposal in the next couple of weeks. If we are successful, the full proposal has to be submitted in May 2021. And we're going to have to work with stakeholders locally to put this together. So stay tuned. Hopefully, you'll be hearing from us on that. And then if our full proposal is successful, we go through a site visit in late 2021, early 2022 with awards in the 6 months or so thereafter. So that's pretty much my story. Thank you very much for listening, and look forward to the discussion, question and answer today, but really going forward, hearing from you and learning from you and doing some cool work, solve this really big problem.
Great, thank you, Dr. Grant, Dr. Edwards. This was a great presentation. I guess with that, I'd like to open up the floor to questions now.
Hi, this is Mike Nordlilly, the Executive Director of ICPRB. I just want to compliment the 2 speakers. Great presentations. I certainly learned a lot. And I had 1 comment and then 2 questions. First one is, when I came on board this job 2 years ago, I met with Chuck Murray, the longtime head of Fairfax Water, and he was about to retire, and I was about to start this position, and I said to him, I have a question for you, sort of like the graduate question. If you had 1 word of advice for me, what would it be? And Chuck Murray said, salt. So this has been on my radar from day 1. My 2 questions are, first of all, wearing my ICPRB hat, have you had any interface with Heidi Maltz of ICPRB and certainly DEQ, because we have had a long-running project called SAMS, Salt Management Strategy, which focuses on the Aquacon Watershed, and a lot of the sort of the methodology you're talking about is something that we developed with DEQ to engage stakeholders in that watershed about ways, and I really liked your comment about building it from the ground up and not from the regulatory side going down. And that was one of the things that we really focused on, was how to engage the public and get them to use less salt, get them to be aware of the dangers of salt, and to make sure that they were all on board with that from the grassroots up, not from a regulatory system down. The second thing is wearing my hat as a board member of the Northern Virginia Regional Park Authority. One of the largest landowners in the Bull Run watershed is the Northern Virginia Regional Park Authority. And also, if you look at the federal partners, certainly on the headwaters of Bull Run being the Manassas Battlefield, so the National Park Service. So the second question is, have you had any connections or interface with those stakeholders, since they are a very significant landowner?
Yeah, that's great set of questions. Mark, do you want me to take that, or would you like to?
No, I'd like you to, yeah.
Okay, that's fine. Yeah, it's funny. I had a meeting when I first arrived here about 1.5 years, 2 years ago with Chuck Murray as well, and I asked him more or less the same question, and he gave me the same answer.
Well,
So yeah, I think that, and frankly, I hadn't looked at the salt issue previously in terms of my professional research. So it was a bit of a risk for me, but I think, probably the smartest thing I've done to, take the jump and leap and really focus on a problem that people care about here. With respect to interfacing with the SAMS effort and the ICPRB, I believe Heidi attended our January workshop, and so I think that we have a very tentative engagement with the ICPRB, and then of course Christina inviting us here today to talk is great start. But the SAMS effort in particular, I'm very much aware of what Sarah Sivers, for example, is leading there. Very interested in the process. I think it's a brilliant process. I think that as we go into phase 2 in particular, where we start looking at watershed sources, thinking about ways to build on what SAMS has done, maybe think about doing some intervention trials, to support some of the recommendations of SAMS would make a ton of sense. In phase 1, we're kind of focusing on the sewer shed, and SAMS is more, as I understand it anyway, kind of road salt focus. So I think that very much on my mind. I'm engaged with Sarah and her team. Thinking about looking at what comes out of the SAMS effort and their report and so on. But maybe not interacting as much right now just because of the focus on the sanitary sewer system. And then the third question, that's brilliant. I hadn't thought about the Park Service. My only excuse is that I arrived 2 years ago, so I'm learning my way around. But yeah, I think that any introductions or meetings that folks think that would be useful for me to have, I would be delighted to do that. So going forward, does that help answer your question?
Yes, very good. Thank you.